energy. So a skier starts from rest on top of a 41.9-meter hill and then skis down a 30-degree incline into a valley and continues up a 32.2-meter high hill. Assuming friction is negligible, find the speed at the bottom of the valley and on top of the next hill. So I'll just draw what that looks like. And remember, when we're talking about the height, we're talking about this right here, not the hypotenuse, because that's how far you're gonna go down. That's how far you're gonna go in total. But when we're talking about height, we're talking about verticality. So, like say if the hypotenuse was 41.9 meters, which is not. This is 41.9 meters, so 1.9. But if this was 41.9 meters, we would have to take the sine of that angle times the hypotenuse to get the height that we need. But since it's not that, we could just leave it as 41.9 and it makes our lives easier. But just know that they might give you the hypotenuse and then you're going to have to find the height. So you'd have to use trig identities and such. And so you're trying to find the speed at the bottom, like right here and right here. So the skier starts from rest. So we have initial gravitational potential energy of mgh, and we'll call it h1 because there's two heights. So h1 will be 41.9. And h2 we'll say is 32.2. So basically, when the skier goes all the way down to the bottom, with respect to the ground, the height is 0, so it would have no gravitational potential energy, and it would be all transferred to kinetic energy. So we see that both of these have a mass, so we can divide mass and those would cancel. So we'd get GH1 equals 1 half V squared. So then we can multiply 2 by both sides. And then take the square root. We get V equals square root of 2GH. So basically what this tells us is he's going to come down with this amount of speed and enter the next hill with that amount of speed. And that's the initial kinetic energy you'll have. And the more energy, the higher you will go up. So, or the higher you go up, and also the faster you'll go. So let's calculate this. So V equals square root of 2 times 9.8 times the height, which is 41.9. So then that would equal 28.66 approximately meters per second. So then we're trying to find the speed on the top of the next hill. So what I'm implying is it's not going to be at rest. So it's going to have both gravitational and potential energy when it reaches the top of the next hill. So we could just take the kinetic energy at the bottom, so 1 half v1 squared, we'll call this, and then it'll equal mg h2, my bad, plus 1/2 mv2 squared. So this is this is what we're trying to find. We're trying to find v2. So we can, again, the masses cancel out, so you get 1/2 v squared equals g h2 plus 1/2 m, wait, no m, v2 squared. Alright, so I'm gonna clear this out and continue. So what we had previously was 1/2 v1 squared equals g h2 plus 1/2 v2 squared. So basically what we can do is multiply by 2 on both sides, so v1 squared equals 2g h2 plus v2 squared. And you can actually see this is one of our kinematics equations. So now we can solve it normally. So v1 squared minus 2gh2. So I subtract 2g8 on both sides to isolate v2 squared. And then you square root both terms. You square root both sides. So then you get v1 squared minus 2gh2 equals v2. So when you plug everything in, you should get a value of around 13.78. And make sure to remember h2 is 32.2 meters, and v1 is the previous answer, what we calculated. Here's another problem. So this is a little review of conservation of momentum. So a 7.9 gram bullet is fired horizontally into a 10.1 kilogram block of wood, and it's embedded into it. After the collision, the block and the bullet slide 15.2 centimeters per second. Find the initial speed of the bullet. So first of all, I'm going to convert into SI units. So 7.9 grams is going to be converted to kilograms. So there's 1 kilogram in 1,000 grams. So then that would give you 0.001 0 7 0.79 kilograms. And then we should convert 15.2 centimeters per second to meters per second. So 15.2 centimeters per second. So there's 100 centimeters in a meter. So that should give you 0.157 meters per second. So now that we're converted to SI units, let's actually solve the problem. So if you recall from conservation of momentum, because it's embedded, they're going to be moving at the same speed after the collision. And initially the block of wood's at rest, so basically we have the initial speed of the bullet times the mass, so that's m1 times v1, and then after the collision they're both moving at the same speed with a combined mass, so that'd be equal to m1 plus m2 times v2. So simply what you have to do is divide by m1 on both sides. Or no, yeah, you divide by m1 on both sides. So you get v1 equals m1 plus m2 over m1 times v2. So when you plug everything in, you should get 194.5 meters per second. And I realized that that should be a 2. Sorry for confusion. Problem is basically a rope is inclined upward at a 55-degree angle and it pulls a suitcase through the airport. The tension of the rope is 26.6 newtons. How much work is done over 122.7 meters? So what this looks like is this is the suitcase and this is the rope, and this is the angle of what they're talking about. So you can have so it basically has a Tx and Ty. So remember, work is only done by the force that is parallel to the displacement, because it's going this way, right? So that means that only the Tx is doing work. Ty is not doing work because the suitcase is not moving up. Instead, what the Ty is doing is it is like altering the normal force, so that plus the normal force equals gravity. But just know that only Tx does work. So basically, like the tension of a rope is 26.6 newtons. That is basically the hypotenuse, not the component. So to find Tx, that's just T cosine theta. And then that's our force. And then our displacement is 122.7 meters, so times delta x, and that gives us our work. And then when you plug everything in, you should get work equals 1872 joules.